So I'm with RTDS Technologies. We are based in Winnipeg, Manitoba, where I'm sitting now, which is a research hub for HVDC technology in Canada. We actually pioneered real-time simulation for the power industry in the 1980s by creating our technology, which is called the RTDS simulator. Today we have over 75 employees, and we have a high level of control over this technology. Our hardware and software developers, power systems modeling team, after-sales support, and even equipment assembly and quality assurance departments are all under one roof in Winnipeg. So before the emergence of real-time simulation, the main way of testing HVDC controls in the lab prior to deployment was by using analog simulators, like the one shown here. These were also known as transient network analyzers. And they were essentially scaled down physical models of the network of interest. So they operated inherently in real time, of course, because they were real analog components. And that meant they could be used to closed loop test external controls. The problem was they were prohibitively expensive and massive. You can see here, they would take up rooms or even entire floors at a time. And maybe more significantly, they were extremely inflexible. So they need to be physically reconfigured for each study, and that could take weeks or even months. So there was a huge need for a more flexible method, and that was really the motivation for developing a digital solution for testing physical controls in a closed loop. So in the 1980s, a group at the Manitoba HVDC Research Centre, which is also the home of the popular PS-CAD software, ran the world's first real-time HVDC simulation. And then they branched off to create RTDS Technologies. So today we have users in over 50 countries. We have four main categories of user: electric utilities, manufacturers, research and learning institutions, and consultants. So here's a look at just a few of over 100 utilities in the world who are using real-time simulation in their labs. And looking here at some manufacturing and research and educational users. So all of the major manufacturers of power system protection and control are users of the RTDS simulator. This is just a subset of our customer base in that area on the left. And these guys have really integrated hardware-in-the-loop testing into their factory acceptance testing of their equipment. And I'll touch more on that later. We also have well over 200 research and educational customers worldwide, a few of which are shown here. There are diverse opportunities to apply this technology, and its uses definitely go beyond HVDC and protection testing. We have customers who have tested wide area measurement, protection, and control schemes, who have validated changes to their distributed energy resource management systems, who have created cyber physical test beds with the simulator, who are testing physical renewable energy inverters in the loop. And we'll take a look at some of these later on. And please feel free to ask or to visit our website if you want more detail on any others. So it's important to understand the type of simulation behind hardware-in-the-loop testing. You might be familiar with a variety of types of simulation, which are chosen based on the phenomena of interest for a particular study. So load flow and transient stability analysis, for example, would give you phasors around the fundamental frequency as an output. And this differentiates them from electromagnetic transient, or EMT simulation, which provides a time-varying instantaneous value output. So for EMT, the simulation output would ideally give you a waveform like the one shown here that matches the current or voltage waveform if it was measured from the real system. And this allows for a much greater depth of analysis over a wide frequency range and the ability to reproduce fast transients on the power system. And the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. And the period of that sampling frequency, or the distance between two consecutive outputs, is called the simulation time step, or delta t, as shown here. So our standard EMT time step is anywhere in the 25 to 50 microsecond range. But if we're interested in representing the high frequency switching behavior of power electronics, say in the tens of kilohertz range, we have to reduce that time step, say to the 1 to 3 microsecond range. So all of those time steps are possible with the RTDS simulator. So why EMT simulation? Well, for steady state analysis, phasor or RMS solutions certainly provide satisfactory results, and traditionally they've been the most widely used type of model from a power systems planning and operations perspective. That being said, there is a lack of ability to capture subcycle phenomena associated with transients, and also the ability to represent low-level controls of inverter-based systems. We've seen increasing evidence that, particularly in systems with a high penetration of converter-connected generation, phasor simulation provides optimistic results. EMT simulation might be preferable or necessary in these situations, as it's more likely to provide realistic results and predict things like control instability reliably. So we know the type of simulation we're dealing with. What does it mean to operate in real time? Well, the real-time aspect is really what separates the RTDS simulator from offline or non-real-time EMT programs, such as PSCAD. And when we say real-time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. So this means the real time for a power system event to occur is equal to the simulation time. A 3-cycle fault on a 60 Hz system, the duration is 0.05 seconds, and that is the quantity of time it would take to simulate that fault on the RTDS simulator. If you've used offline EMT programs, you know they run on standard PCs rather than using dedicated parallel processing simulation hardware, and the time they need to complete these simulations is much greater. And that's one of the principal advantages to making the switch to real-time simulation is the efficiency. And simulating a single fault might not be so onerous, but when you're running longer simulations, including slower acting dynamics and control, or running high volumes of simulations, the simulation time may become daunting using an offline tool, and running in real time can be tens or hundreds of times faster for complex networks. Okay, the other main advantage of running simulations in real time is the ability to connect external hardware to the simulation in order to test it in a closed loop. So closing a loop means not only observing the response of the device to an imposed signal, but also interfacing that device's response back into the simulated network. And this type of testing, also called hardware in the loop testing, is only possible if we are updating the inputs and outputs of our simulation continuously in real time. It's not possible with an offline simulation or with open loop testing tools like a relay test set. While test sets will remain an important tool for supporting the commissioning process, they lack the flexibility to test multiple devices at once or to allow for detailed modeling of the network, for example, power electronics. In a modern system with distributed energy resources or multiple tiers of control, our users find that it's valuable to be able to test interoperability and interactions between different systems. And here, the test doesn't end when the relay trips. It allows you to observe the dynamic response of the network, including the response of other automation components as well. So to do nodal analysis on the power system with a 50 or 25 or 1 microsecond time step is very intensive. And of course, the processing power required increases with the size and complexity of the network to simulate. To achieve this, the RTDS simulator is built on dedicated parallel processing hardware, specifically integrated for the real-time application. So our current hardware generation is based on IBM's Power 8 processor, that's a multi-core processor, and we've developed it at the embedded level, so there's no underlying operating system. We run our code bare metal on the processor for higher efficiency. And we achieve modularity in the simulation through core licensing. So the quantity of cores licensed on a given unit determines the size and complexity of the simulation it can run. And multiple units can be connected together to achieve larger simulations as well. We use parallel processing on 2 levels. Inside a given unit, different cores of the processor are each dedicated to a different task in parallel to carry out the simulation. And as the network size increases, it's possible to exceed the processing resources for one unit while maintaining the desired time step. And when that occurs, you can split the network into connected subsystems over multiple units. So we essentially have parallel processing both within each unit and between units for larger systems. In order to connect the simulation to external equipment to realize our closed loop, We use analog and digital input and output cards. So here, for example, you see an analog output card, which has 16-bit digital to analog converters, and it might be used to send power system voltages and currents to a relay, for example. Similarly, we have our digital I/O cards. A typical application of the digital input card, for example, would be to bring external firing pulses into the simulation. The interface with external equipment can also be created based on standard compliant communication. To do so, we use this network interface card. So this card takes power system simulation data, assembles it into standard compliant packets, and then sends those out via Ethernet. And it can also, similarly, unpack the inputs coming from devices under test. And it can directly stream the protocols listed here in real time. So I think it's useful to see how all these things work together to create a hardware-in-the-loop testbed. Here the example is for two relays. So you can see we have a simple simulated system in the box, a transmission line that we can throw a fault on, instrument transformers, breakers, and sources. And we're taking our voltage and currents from the CTs and CVTs, sending it out of the simulation via analog output, then applying those signals to the relay inputs via a power amplifier, which allows us to provide secondary level signals to the relay. And then the relay contacts can then actually be wired back into the simulated breaker via digital input. And breaker status can, of course, be sent out via digital output. And this whole interface could also be achieved using IEC 61850.